In example number 10, we have a pilot flying in a vertical loop. At the top of the loop, the problem tells us that the plane is completely upside down, and for a very split instant, the pilot is hanging freely. There's no force from the seat belt. There's also no force from the seat, which we may have called normal force. That means the only force acting on our pilot is the force of gravity, and therefore the force of gravity is responsible for the centripetal force. We'll write that down, indicating that Fg, the force of gravity, is equal to Fc, the centripetal force. Well, we know the force of gravity is mass times gravitational acceleration, and we know centripetal force is mass times centripetal acceleration. Notice there's a mass on each side of the equation, so we could divide both sides by mass, and so mass cancels out. That tells me that the gravitational acceleration, which we know has a magnitude of 9.8 meters per second squared, is equal to the centripetal acceleration. Well, we know the centripetal acceleration equation is velocity squared divided by radius. Radius is the thing we're looking for in this problem. Radius is equal to velocity squared divided by centripetal acceleration. In the problem, we're told that his airspeed indicator is reading 120 meters per second. So we plug that in for the speed, 120 meters per second. We square it, that's very important, and then we plug in 9.8 meters per second squared for the centripetal acceleration. And we find out that the radius of this path is 1,469 meters. You could also express that in kilometers as 1.469 kilometers. It's a very large radius, but he's going at a very high speed. Moving on to the next problem, example number 11. In this problem, we have a ball that is swung vertically. It's on the end of a 0.5 meter cord. It's swung in uniform circular motion at a speed of 2.4 meters per second, and we want to know the tension in the cord at the bottom of the ball's motion. I'm going to take a moment to draw a picture of this. So, there's the path, and here's the ball here. The next thing I'm going to do is draw a free body diagram. You'll understand why I'm doing this in a moment. So here's the dot representing my ball. I have gravity acting downward, as it always does, and tension acts upward. Centripetal force is equal to the sum of all forces that are parallel to the radius. Well, the radius is in the y direction. It's up and down here. Both of these two forces are also in that direction. So the sum of these two forces is equal to the centripetal force. In this case, the centripetal force points upwards. That's another important fact. So, centripetal force is equal to tension plus gravitational force. Tension is what I'm looking for. So if I solve for tension, I find the tension is equal to centripetal force minus gravitational force. Centripetal force is mass times centripetal acceleration. Gravitational force is mass times gravitational acceleration. Let's go ahead and find the centripetal acceleration based on the information we're given. We know that the speed is 2.4 meters per second, and the radius is going to be 0.5 meters. As you can see in my diagram here, that's the length of the cord. It also happens to be the radius of my path. So, centripetal acceleration, which is velocity squared over radius, is equal to 2.4 meters per second squared divided by 0.5 meters. That gives us 11.52 meters per second squared. So plugging numbers in here, the mass of my thing is 1.13 kilograms. So I multiply that by 11.52 meters per second squared minus 1.13 kilograms times negative 9.8 meters per second squared. Plug all those numbers into my calculator, and I find that the tension is equal to 24.09 newtons.